Hello everyone. In this video we are going to use our Excel sheet in order to help us do a regression analysis. Okay, let's take a look at what's going on. So we see that Megan is working with NASA to monitor a rover that has recently landed on Mars. Her job is to track the weather to determine whether they should or when they should deploy shields over the rover's sensors. Unfortunately, if she puts the shields up, they are unable to perform the mission experiments. But if she leaves them down during intense dust storms, the sensors will be permanently damaged. Her main concern is about the amount of particles in the atmosphere during the dust storms. Instead of sitting up all time with her finger hovering over the Shield Now button, it would be too late anyway to protect the sensors due to the time it would take to send the signal. She thought it would be way better just to set up an algorithm to tell the rover when to shut down itself. Measuring wind speed is one of the few sensors that is safe to have always safe to have running. As such, she wants to be able to predict the amount of particulates in the air based on the wind speed. So she starts taking measurements and wants to see if there is a relationship between airspeed and the number of particulates in the air. She tests at the significance level of 0.08. Okay, so we are ready to go. We're trying to predict the particulates in the air by measuring the wind speed. And so if we can get some sort of relationship here going, then we can just have this algorithm run and it will protect the rover sensors on its own. Okay, so we know that the alpha level right here is 0.08. And then we need to put in our predictor X in column B and the response Y in column C. And if we look at our data, notice that our particulates are actually in the wrong order here from what we need over here. Don't worry, we have this button called swap X and Y. So we're going to copy your data, copy it, put it in here, and let's do our paste special. And here we see, okay, so we have the particulates, and right now they're being the predictor and they are predicting the response of the wind speed, and we need to flip that. So we're going to click swap X and Y, and now we have wind speed in our B column and our particulates in our C column. So that's all that you have to do. If you wind up having them in the wrong column, you just switch them. Make sure that our x-axis, which is our predictor, is in column B, and the response is in column Y. Okay, now that we have our data in, we can take a look at our residual plots and our QQ plots, and we can go through this. So like, what type of data are we dealing with? We're dealing with numerical by numerical, right? We've got one piece of numerical data predicting another. The predictor is our wind speed, and the response is the particulates in the air. The population of interest is the atmospheric conditions near the rover, so that's what we're interested in. And then the parameter of interest is going to be the true mean particles per cubic centimeter. Okay, so here we have our residual plot, and notice that we have it over here as well. And do we have any problems here? Do we have any problems with linearity, or do we see a pattern going on? It's like no pattern. Independence, do we see any clustering? No clustering. Do we see constant variance? Yeah, we don't see any like fanning where it starts off tight and it gets really wide. Is it centered about 0? And the answer, well, this graph is really hard to see it. But if you come over here, we are centered about 0. And is it normal? Now, we could look at it here in the residuals, but it's kind of tough to see. So that's why we go to our QQ plot or our Shapiro-Wilks test. And the Shapiro-Wilks says, yes, it's normal. And the QQ plot, notice how the dots are pretty much on the line, maybe a little bit of a squiggle, but not bad. So we would say that none of these are an issue. The method that we should be using for our analysis is going to be regression. And so the distribution that we're going to be using is an F-test, just like we were doing in ANOVA. Okay, so let's go down and let's look at our null and our alternative hypothesis. So the null hypothesis is that beta 1, which is the true slope, is going to be equal to 0. There's no relationship. And then beta 1, we think that there is a relationship. So we're going to say not equals to 0. All right, so those are our null and alternative. We need to select the appropriate scatter plot. So if we look at the scatter plot, this was our scatter plot. And so this is the correct response right here. And the relationship here is going to be a positive response because it is going from low left to high right. If it went high left to low right, that would be negative. And if it was flat, it would be like neutral, and inverse and polynomial are just there to throw you off. Okay, so identify alpha, 0.08. Great. Now we've got collect our data and our test statistics. So B0 is our sample y-intercept, and it says 1.1587, and that's where we get it from our coefficient here of our intercept. And then the slope that we predicted is this 3.5069, which is right here with our coefficient. R squared is the percent of variability that the model accounts for in the data. And we get that from right up here from our R-squared value. Our p-value, we come and look at our F statistic, and if you notice, we have a gigantic F statistic and a tiny p-value. So our p-value is equal to essentially 0. And then our p-value is going to be less than our alpha. Okay, so at this point, we want to know our confidence interval, or where do we think that the true slope is between? And we think that it's somewhere between 3.4 and 3.6. And we grab those because we're interested in the slope information, not in the intercept confidence interval. So just be sure that you're grabbing it from the slope. And then our decision is that we're going to reject the null. And if we reject the null, we're going to want this one. So we have collected sufficient evidence. F 125. Okay, where did that 125 come from? Remember, degrees of freedom, our first one, and then the second one, 1 and 25, with our F value, 3705. And then we have our p-value, which is less than 0.001, and our alpha is 0.08, to reject the claim that there's no relationship between the wind speed and the number of particulates in the air, and instead claim that there is a relationship between the two. And our model is able to account for 99.3298% of variability in the data, which is a very good model. That came from that R-squared value. That's how you interpret the R-squared. Then we are 92% confident that for every 1 km/h increase in the wind speed, the true mean number of particulates per cubic centimeter increases by somewhere between 3.4 and 3.6 particulates per cubic centimeter. So that's how you do a regression analysis using our tools in Excel. Good luck on doing it on your own assignments.